And as usual, we're going to see that if you do something outside of the function, it affects it vertically. Do something inside of the function, it affects it horizontally. That's kind of always the thing that I like to keep in mind. So when you multiply by a number, what does that do to the graph? Well, it stretches it. Multiplying a number by a number outside of the function stretches the graph. I don't love this pen already. This is going to stretch the graph by a factor of a if a is bigger than 1. And it's going to compress the graph by a factor of a. Oh, I forgot an important word. If a is between 0 and 1. Now, there's one word I forgot, which I need to include. It stretches the graph vertically. Sorry about that. And it compresses the graph vertically. And then just as an aside.
Hey, James.
Yeah.
James.
Yes.
I can't hear anything. I don't know if you saw my chat or not, and I'm wondering if it's just me.
So some people are saying they can hear me. Yeah, one person is saying they can hear me. Who else cannot hear me? That's a great question to ask. Who can't hear me? Sorry, one sec. Oh, sorry. Technology. It's great when it works. One second, everybody. Sorry. I don't know what's going on. It might. So. All right, I'm gonna keep going. I'm trying to talk to the person who can't hear me. It's just the way my brain is working. Sorry. So, let's see here. What was I saying? Oh yeah, I was gonna say, if the value of a is negative, then we're gonna get a vertical flip additionally. Just like before. Yeah. So one more time. Yeah, so I've written a as if it's positive, but then what we're going to see is that essentially if your a value is a large number, bigger than 1 or more negative than -1, we're going to get a stretch. It's just that it's also negative, you're going to get the flip. So what I would encourage, what we're really going to do is we're going to kind of look at the negative, if there is one, separate from the constant we multiply by. And then the same kind of thing is going to be true for horizontal, except it's going to be kind of counterintuitive, meaning we're going to get a, let's give ourselves some room here. This is going to stretch the graph horizontally if your b value is small. So if 0 is between b and 1. Sorry, b is between 0 and 1. And the reason that's the case is, well, again, what I'm thinking about is I need the x values, or I just need the inputs to be kind of the same as they were before to get those corresponding outputs. So if b is a small number, then x has to be large to counteract that. So when you have a small coefficient there on x, the x values get bigger and bigger, and it stretches the graph horizontally, because if x is getting larger, you're moving further left or further right. Sorry, further left or further right. We'll see an example in a moment. And then likewise, if we're going to compression horizontally if b is larger than 1. And then again, if b were to be negative, we would also get a flip across the y-axis. All right. So it's great to see some words, but let's actually go ahead and do some examples because that's really how we're going to see things. And we're going to draw all the in-between graphs here. So let's start with the parent graph. What is my parent graph? Well, it's y equal to the absolute value of x. We're going to take that absolute value function and we're going to modify it. So here is my parent graph. What should I do next? Should I think about the stretching by a factor of 3 or the shifting down by 4? Well, it's a good question. And the way I always think about it usually is you kind of want to work from x out. So if you were kind of operating on x or trying to do something to x, first you take the absolute value, and then what would you do next? Would you multiply by 3 or would you subtract 4? We'd multiply by 3. So that's what we're going to think about doing next. We're going to multiply by 3. So let's, in red, look at 3 times that. So the y values are going to be 3 times as big as they were. So instead of having the point 1, 1, I'm going to have the point 1, 3. Instead of having the point 2, 2, I'm going to have the point 2, 6. And the same on the left, -1, +3, -2, +6. Whoops, turning it off a little bit there. So here's my vertically stretched absolute value graph, right? And really, I can kind of think of, we're really pulling the graph up. So this point is getting pulled away from the x-axis, and this point is getting pulled away from the x-axis by a factor of 3. And then we're going to shift down by 4. So move everything down 1, 2, 3, 4. I usually am thinking about kind of where the most important point is moving to, like the vertex of a parabola or an absolute value, or kind of where the origin point usually moves to is what I'm often thinking about. So now I'm just shifting all my points down by 4. So this point 1, 3 is going to be 1, -1. This point 2, 6 is going to be 2, 2. Looks like this. So there's my final graph in green. Y equal to 3 times the absolute value of x minus 4. A couple things people might ask. Where are the intercepts, right? That's almost always, if someone's going to ask you anything about a graph, they're most likely going to ask you, where are the intercepts of this graph? So what's the y-intercept? Well, how do we find the y-intercept? Same as it ever was, we set x equal to 0. And if we set x equal to 0, we're going to get y equal to 3 times the absolute value of 0 minus 4, which is just -4. Which we already knew, right? I mean, that's kind of part of the graphing of it. We're like, oh yeah, we shifted that thing down by 4. We knew that our y-intercept was already 0, -4. The x-intercepts, on the other hand, we don't really know by looking at it. They look like they're somewhere between 1 and 2. And if we actually wanted to find them, we would set the whole thing equal to 0. We're setting 3 times the absolute value of x minus 4 equal to 0. I have 3 times the absolute value of x equal to 4. And get the absolute value of x equal to 4/3, which means x could be either +4/3 or -4/3. Which seems reasonable, right? That looks like where those points are about. Again, my graphs, your graphs are not going to be perfect. They're going to be okay, right? But at least mine aren't going to be perfect. Yours good. I've seen some very nice graphs from you all. My graphs, on the other hand, are so-so. Okay. You could think of it that way for this particular graph, yeah. Right, because an absolute value does have, like, you have slope either way. It just, you're going over 1 up 3, but you're also going over 1 to the left up 3. So you kind of go over 1 and up either way. Yeah. Excellent question. Why is it negative and positive? Well, first of all, we can look at the graph and see it's definitely having a negative and a positive x-intercept. But if you're saying the absolute value of x or the absolute value of something is equal to a number, well, when you take the absolute value of something, no matter whether your input is positive or negative, it spits out a positive number. So what is the absolute value of 5? What's the absolute value of negative 5? Also 5. So if I'm trying to figure out what numbers, if I take the absolute value of them, they equal 4/3, well, the absolute value of 4/3 is 4/3, and the absolute value of negative 4/3 is also 4/3. So that's typically what happens when you're trying to solve an absolute value equation, is that the insides can be either the positive value it's equal to or the negative value it's equal to. All right, good questions. No, you won't have to show. So someone asked on the quiz, will you need to show how we transform the graph, like having 3 graphs in example 1? No, you won't have to show all the graphs, but I might ask you a question like, what things do you need to do to this graph to transform it in the way that's being asked? If that's a hand over here. I'm sorry, I missed something. Can you say that again?
Like, it's the case on the right side, like if you go up, it's this. Or here.
I guess I'm not sure what you're asking.
Well, like, so it's multiplying by a number inside the function despite that the 3 looks like
So well, no, so this is where things get a little bit kind of, you could see it either way is the issue here. So I'm seeing it as the 3 being outside of the function. The function is the absolute value and the 3 is happening after that. But it would be equivalent to if the 3 was inside. So you could either view, like from the black absolute value function to the red one, you could either think of that as how I thought of it, a vertical stretch, but you could also think of it as a horizontal smush. Right? You could think you're pushing that in instead of stretching it up. And that's unfortunately kind of one of it's the nature of this process, is that oftentimes a vertical stretch looks equivalent to a horizontal compression, or a horizontal stretch looks equivalent to a vertical compression. But so typically what I'm going to try and see is, does it look like it's happening inside or outside? And here I would say, well, that 3 is outside of the absolute value. But I will point out this graph would be the same as, oh, this pen is terrible. My pen's terrible. That would be the same time as the absolute value of 3x minus 4. So you could totally think of it as a horizontal compression instead of a vertical stretch. Okay, let's look at some more examples. I got papers everywhere. So let's graph the square root of 1/4 x. Now, the way it's written, are we multiplying by 1/4 inside or outside of the function? Definitely inside. So we're expecting a horizontal stretch because we're multiplying by a number that's small, or as I like to think of it, the x values have to get bigger to compensate. Here's how, before we graph this, I'm going to plot some points, or I'm going to make a table with some points so I can kind of show you what I mean. Here's the usual, parent function. Right, if we're looking at y equal to the square root of x, the points we would normally think about plotting are the easy ones, like x equal to 0 and the square root of 0 being 0, and x equal to 1 and the square root of 1 being 1, and x equal to 4 and the square root of 4 being 2. And then you could plug in 9 and get 3, but so there's your usual parent graph. And then we'd also like to see how this 1/4 really modifies things. So if I'm trying to have enough room to write things, what I would really like is for the things I'm taking the square root of to still be nice numbers. So I would really like my 1/4 x to still be the numbers like 0, 1, 4, and 9. Because those are the numbers that if I take the square root of them, I still get nice outputs. The square root of 0 is still 0, square root of 1 is still 1, square root of 4 is still 2, square root of 9 is still 3. But so those are the y values I want. But these aren't the x values I'm going to graph, right? Because those are the 1/4 x values. So if 1/4 x is equal to 0, what's x going to be? Okay, well, that's not that exciting. It's also 0. But if 1/4 x is equal to 1, what did x need to be? 4 times as big. And if 1/4 x equals 4, x had to be 4 times as big. And if 1/4 x equals 9, x had to be 36. So this is what I'm saying by we have a horizontal stretch, is the x values have to be 4 times as large as they were to get the same corresponding y values. So these are the things I'm plotting. Those are my x values, those are my y values. So I'm going to get 0, 0, but then instead of 1, 1, I'm going to get 4, 1. And already I'm kind of off the chart, right? Like I could try to graph 16, 2, but it's like way over there. And this is a horizontal stretch, right? We are pulling all of these points to the right by a factor of 2. Okay, and now for the, I don't know if I want to say bad news, but the unfortunate news is that you could also think of this as a vertical compression. What's the square root of 1/4? What is the square root of 1/4? 1/2. So you could also write this as 1/2 times the square root of x. And now the 1/2 is on the outside. And you say, oh, we're smushing down by a factor of 2, which you can also still kind of see, right? I mean, you could think of this graph as pushing down to get to the green graph instead of pulling right to get to the green graph. So the sad kind of truth about this is that vertical things and horizontal things kind of look like each other, right? Vertical compressions look like horizontal stretches, and vertical stretches look like horizontal compressions. There's not really anything nice to say about that. That's just kind of how it is. But I think you're usually safe or relatively safe thinking about, well, if it's inside the function, I'm just going to think about it horizontally. If it's outside the function, I'm going to think about it vertically. But if you prefer, right, you could take this and rewrite it this way to think about it the way you like to think about it better. I will also say we could graph another one. Let's graph g of x equal to the square root of 2x. Sorry, thank you. So that's going to be a horizontal compression by a factor of 1/2, right? Because we're multiplying on the inside by a number that's larger than 1. So my x values are going to be, instead of 4 times as big as they needed to be, they're going to be half as big as they needed to be. So instead of getting the point 1, 1, I'm going to get the point 1/2, 1. And instead of and I should make a little table because why not? You are not required to make the tables. I'm just showing them to you so you can really see what's happening. So if x is 1/2, I get the square root of 1, which is 1. And if x is, well, instead of x being 4, half of 4 is 2. So if x is 2, the square root of 2 times 2 is 2. And instead of x being 9, which is the next nice point, I want 9/2, because the square root of 2 times 9/2 is the square root of 9, which is 3. So all my x values are half as big as they were before to get what we need for the output. Question? Sure. Could you? Well, so this graph in black is the parent graph, y equal to the square root of x. And this graph in green is the transformed y equal to the square root of 1/4 x. You're welcome. And then this graph in red is the one we just did. It's y equal to the square root of 2x. And again, you can think of this as being, for me, it's easier for me to see things vertically. So it's harder for me to be like, oh yeah, I'm pushing, right? I'm pushing this graph that way towards the y-axis. But that's what's happening. When we have a horizontal compression, we are pushing things towards the y-axis. When we have the horizontal stretch, we were pulling things away from the y-axis.
What's the point for 4 for the y equals
The point for 4. Sorry. You mean, oh, so at this point here? So that's 9/2 for x, which is 4.5. No problem. Other questions? Tyler, I'm assuming you can hear me. I hope. You haven't said anything, so. If not, you can always watch the video later, assuming the sound works. Okay. So putting it all together, you're probably never, I feel like this is, I don't know about all this, but we'll talk about it for a second. So we see all the things we've already seen. This is going to indicate a vertical stretch or compression. This is going to be a vertical shift. So again, the things outside the function are affecting it vertically. And then inside the function, that constant there is going to give you your horizontal stretch or compression. I know it's hard with my big hands covering everything up. And then this value here is going to give you your horizontal shift. And let's be a little more specific, right? So vertical shift, if D is positive, you're going to be going up. If D is negative, you're going to be shifting down. In a similar way, if C is positive, you're going to be shifting which way? Left. And if C is negative, you're going to be shifting right. Which we saw last time. Right, so if you add on the inside, X has to be less than it was, so we shift it left. If you subtract on the inside, X has to be greater than it was, so we shift it right. And so that's kind of why the horizontal stuff is maybe what I often say is counterintuitive, because you're having to adjust X to counteract what you're doing on the inside. So if you're adding stuff on the inside, you're making X smaller to counteract that. If you're multiplying by a number that's big on the inside, you're making X shrink to counteract that. And I feel like we could write stuff here, but it's really just the same stuff we wrote before. It feels silly to rewrite the same things, so I don't think I'm going to do that. I will also point out the notes from last time I taught this section that are posted already have a little bit more explicit writing on them. So if you're looking for more things to be said, I would look there just because I've already written nice things. But yeah, I think it's silly to repeat that. So let's look at some more examples. And the order we're going to look for things in is, I think you can see this. So the order of transformations is the following. So first you want to look for a horizontal shift. Then you want to look for a horizontal reflection or stretch. There's a better word. Sorry, there is a better word, but I can't remember what it is right now. There's a word that's like for stretch or compression, which is I don't remember what it is. No, transformation is the word that kind of covers everything. Dilation, that's the word that they use for stretch. So dilation means you can make it bigger by a factor or smaller by a factor. So I guess I'll use that fancy word because I don't want to write all the things. So first we look for a shift horizontally, then we look for a stretch or a compression or a reflection, right? So stretch, reflection, compression are all tied up in the same thing, which is the thing you're multiplying by on the inside. And then after that, we look for the vertical reflection or dilation. My writing feels extra not good today. And then lastly, we look for the vertical shift. That's the order we're going to look for things in. So let's look at this first example. Well, this next is not the first example. So horizontal shift. Am I adding or subtracting anything on the inside? No. So then I'm going to look for a horizontal reflection or dilation. So on the inside, I'm not multiplying by a negative, so I don't have a reflection horizontally, but I am multiplying by 2 on the inside. So that's going to be a horizontal compression or stretch. Compression. So remember, the horizontal one's always kind of the opposite of what you might immediately think it is. Right? We're multiplying by 2 on the inside, which means x has to be smaller. So you have a horizontal compression by a factor of 2. And then as we work our way out, this negative sign here is going to give us a vertical reflection. And then finally, this -3 is going to give us a downward shift. So I'm going to draw all the pieces because I think I should. So I need more colors. We'll start with the parent graph in blue. Here's your good old square root of x. I should label it. I don't need you to draw all these graphs from me. You're certainly welcome to if it helps you see things and learn things, but I don't need that from you unless you're specifically being asked to do that. All right, we're going to compress horizontally by a factor of 2. So all of my x values just become half of what they were. So instead of 0, 0, I get 0, 0. Instead of 1, 1, I get 1/2 1. Instead of 4, 2, I get 2, 2. Instead of 9, 3, I get 9/2 3. So there is my y equal to the square root of 2x compressed in. And now we're going to flip it. So it's going to flip down across the x-axis. And then finally, we're going to shift it down 3. So instead of having 0, 0, now we have 0, -3. Instead of having 1/2 -1, I have 1/2 -4. All these points just go down 3. There's your final result. Some interesting questions we could ask. Oh, I should write them in. Sorry, I forgot to write what they were. This is y equal to the negative square root of 2x. And this is y equal to the negative square root of 2x minus 3. So there wasn't a horizontal reflection in this one. We have a vertical reflection where we flip the graph over. You would get a horizontal reflection if you had a negative inside the function. So if that was like a negative 2x, you would also have flipped this across the y-axis, but we don't. Yeah. Something else. Oh, I would know what I was going to say. If we look at the graph, what's the domain? What are the allowed x values? Well, it looks like x can be greater than or equal to 0. That's actually not the question I'm super interested in asking. I'm really actually more interested in talking about the range. So if we look at the range of this, what's the highest y value we get for the final graph? So Yeah, -3. And what's the lowest y value we get? I mean, I know I've only graphed some of it, but this keeps going down and down and down and down and down forever and ever and ever. So the lowest y value, we don't really get a lowest y value. It keeps going down towards negative infinity. So the range here would be y is less than or equal to -3, or written as an interval, everything from negative infinity to -3. That's the range of this function. What time is it? Okay. Questions? It's okay. It's okay to ask questions. You guys asking me questions too? All right. Let's look at another example. So again, we're just going to take this and shift it. So when I'm looking at this, I'm looking at the x and then seeing what's happening to x in the order of operations kind of way. So first for x here, I'm subtracting 4, and I'm squaring that quantity. Well, yeah, then I guess I should start over. That's okay. I suppose I should really try to identify the parent function first, which is where I should really start. So what's my parent function here? Right. 1 over x squared. And then what am I first doing to x? I'm first subtracting 4. That's going to shift it right. 4. Okay. And then what's the only other thing we have to worry about? The negative. What's that negative going to do? Is that negative on the outside or the inside? It is on the outside. I know that's not always a great question, but basically the question is the negative being a negative x or a negative of the entire thing? Here it's the negative of the entire thing, because you could totally write that as -1 over x minus 4 squared. That's a negative on the outside. So that's going to be a vertical reflection. So I'm going to not graph the original graphs first, just so I can show you what you have to do or what you don't have to do. So I'm going to think about shifting. Well, I'm going to think about the parent graph, which is this one. Maybe I should draw the parent graph first. So my parent graph, I always think about graphing these 2 points, 1, 1, and -1, 1. And then this 1 over x squared graph looks like this. Has a vertical asymptote at 0, has a horizontal asymptote at 0. And now we're going to shift it 4 to the right. And I should label it. So notably, when we're shifting things left or right or up or down, I like to think about kind of what happens to the important features. So if I'm shifting a parabola, I'm thinking about where the vertex goes. If I'm shifting the square root function, I'm thinking about where kind of the origin point goes. Now there aren't other points, but that's kind of the kind of most visible point of the graph. So if I'm shifting this graph, I'm thinking about what's happening to the vertical asymptote. So I do have a vertical asymptote at 0. Now it's going to move 4 to the right along with everything else. So my new vertical asymptote is going to be x equal to 4. And so then this point here at -1, 1 is going to shift 4 to the right. This point here at +1, 1 is going to shift 4 to the right. So my graph is going to look something like this. Try your best. It's not easy to graph this, but try your best to make sure it doesn't actually cross the x-axis. Right? It shouldn't touch the x-axis. It should always be above it. But it's hard when you draw those horizontal asymptotes. Like sometimes you're like, oh, actually, no. So it's okay if you make a tiny mistake in your graphing. And then finally, we're going to reflect that over the x-axis. We have a vertical reflection. So all that's going to come down. Oh, okay. Green fingers. So I'm going to have the same looking graph, but now My points are down here, and it's going to do this kind of deal. Oh, come on. So that's y equal to -1 over x minus 4 squared. Okay. More examples. Yeah. Okay, say that one more time. I didn't mean that point. So the answer is I. What I mean by that is I need the points for myself to make sure I graph the graph reasonably well. But honestly, if I were actually graphing this, like so part of the issue for me is I've got this grid here that I'm trying to kind of not totally screw up. But if I was graphing this without like graphing paper, I'd be like, okay, I know I'm going to go 4 to the right, and then I'm going to flip it over. Call that a day. Now that, I mean, I tried to do a little bit better of a job, but like, that's kind of, I mean, and I might be like, okay, I have a point there. It's 5, -1. I have a point there. Again, this graph being not super excellent. Those are kind of the 2 points I'm thinking about how they're getting transformed. So your graph does not need to be super extra precise like this. You're totally fine not plotting points. If someone wanted you to plot a point, they'd probably ask you on this what your y-intercept was. And then you would find that y-intercept by setting x equal to 0. So you get 1 over 0 minus 4 squared equals 1 over 16. So again, to answer your question, you don't have to plot all these points that I am plotting. I'm just trying to show you a nice looking graph, really. But yeah, it's a very good point, is I really don't want you to get hung up on being as precise as I am being. And I wish I could model that better for you, but I feel like I need to draw the graph nicely so that you can actually see how it looks. But yeah, I think you could draw less nice graphs is what I should really be saying. I mean, try to make them look decent, but they don't have to be perfect. Not that mine are. Let's look at another example here. 1/3 x minus 1 minus, sorry, the absolute value of 1/3 x minus 1 minus 4. Oh, sorry about that, of course. There we go. The absolute value of 1/3 x minus 1 minus 4. Now, this one has kind of an extra bit of trickiness to it. The horizontal shift isn't 1 to the right, which is kind of a bummer. The problem is when you have a horizontal shift and a horizontal dilation, the dilation affects the shift, or the shift affects the dilation. What we need to do is we need to kind of factor out that 1/3 from the inside. So here's how we're going to rewrite this. We're going to write this as the absolute value of 1/3 times something minus 4. So I factored out a 1/3 from 1/3 x. I'm left with x. And if you factor out a 1/3 from 1, or if you divide 1 by 1/3, what do you get? You get 3. So the shift to the right is really a shift of 3 to the right, not a shift of 1 to the right. I did 1 divided by 1/3, which is 1 times 3 over 1. So what I'm really thinking of is, I know I want this 1/3 factor out in front, and I know that if I multiply it back through, 1/3 times -3 gives me the -1 that I started with. So here's what we've got. We're going to shift it right by 3. We're going to, is that a horizontal stretch or a horizontal compression? the horizontal stretch by a factor of 3. And then finally, we're going to shift it down 4. All right, so let me try and not be super extra precise when I draw this. See if I can manage that. Here's my parent function. Oops, already not very precise. It's okay. And then I'm going to first shift it right 3. Interesting. Which I did in red. So there's y equal to the absolute value of x minus 3. And then I'm going to multiply that by a factor of 1/3 on the inside. So I'm going to stretch it horizontally, meaning I'm pulling it away. This is where, yeah. Let's see. There's that graph stretched by a factor of 3 horizontally. Shouldn't minus 3 be minus 1? So it is a minus 1 if you distribute the 1/3 back to each term. But the reason we're factoring out that 1/3 is so that we can see what the horizontal shift actually is. And then finally, we're going to pull this all down by 4. So this point here comes down here. It looks like that. And it does cross the x-axis. It's just a lot more drawing to do. So we could keep going if you really wanted to. Oh, you're right. I drew it wrong. Yes, you're totally right. I drew it wrong. So bummer. Sucks when you draw it wrong. Not you. Yeah. And so I'm thinking about where that kind of origin point ends up. Oh yeah, x needs to be 3, and then y is going to be -4. Right? I've shifted 3 to the right and 4 down. And I've stretched it by a factor of 3 horizontally. Can you explain the step in green? Yeah, so the step in green, we've taken the red graph, our y equals the absolute value of x minus 3, and we have stretched it out vertically by a factor of 3. Yeah. And I feel like it might be hard to see what's going on there. And that's because it is. One sec. Because, yeah, I don't love that either. So I feel like I'm trying to kind of adhere to some rules that I don't particularly love, to be honest. These are rules that work, but if I was graphing this, I probably wouldn't do all this. Right? I would probably be like, okay, well, let me think. It's the absolute value function. And I've got 1/3 x minus 1. And I would really love these here. So here's what I mean by this. Sorry, all sums. I know it's an absolute value function. I know it's opening upwards because I haven't flipped it downwards, that there's no horizontal or vertical reflections. And I'm kind of really thinking about, okay, the one thing I do think you do want to do here is rewrite it as 1/3 times x minus 3 minus 4. But if I wanted to graph this efficiently, even though I know there's a stretch and a compression and a shift, sorry, there's a stretch and a shift and another shift, I kind of want to just think about where's the bottom of this absolute value. I know it's got a V shape, and the bottom or the vertex is going to be when x is 3, because that's going to make this as small as possible, and when you're going to get y equal to -4. Great, there's the bottom of my V. Yes, we do call it the vertex. And then if I wanted other points, I might just plot them, meaning it's going to be very, very easy to plot the y-intercept. If I set x equal to 0, I'm going to get y equal to the absolute value of 1/3 times 0 minus 1 minus 4, which is just the absolute value of -1 minus 4, which is -3. And then I can see, oh, I'm going to look like that. And then it should look the same the other direction. So there's kind of two things at play here. One thing is, we want you to be aware of these transformations because they're a useful way of seeing how functions work. But it's not typically how people actually go about graphing things all the time. I would say yes to the shift. So okay, the truth is, it's the stretching and compressing that's terrible, in my opinion. Like definitely shifting left and right, up and down, not that bad. Reflecting vertically, horizontally, not that bad. But the stretching part is always like, this is just terrible. So what we'll see is when we start graphing much later on, like the last third of the quarter, I know much later on, like in 4 weeks, right? Much later on, when we're graphing trigonometric functions, the stretching and compression, and so stretching and compressing will make a lot more sense as to why we might look at something like that. But for these graphs, it's really more try to make it look decent by doing these things. But I don't want you to feel so beholden to them. What I really want for you is to be able to graph this without doing a ton of work. So I don't know if I feel like I've done a great job of really displaying that. I think I could improve on how I've done today. Like I feel like, oh, okay. But what I want you to take away is, I don't mean for graphing to be hard. I don't mean for this process to be like, oh, there's a ton of things you have to do. I really want you to be able to say like, okay, here's this graph 1/2 times x minus 2 cubed. I'm taking my cubic graph. I'm shifting it 2 to the what? To the right. So I know my 0 point is going to move 2 to the right. And then it's going to squash by a factor of 1/2. So instead of going, over 1 and up 1, which is what we usually do for the cubic graph, I'm going to go over 1 and up not quite as much. So it's going to kind of look like this. And I would have some y-intercept. But I don't, that's really like, that's what I want, right? I want you to give me that much information. I don't need that much more. So we shifted to right, and we did a vertical compression. And if I was, what I probably would have done really is I would have found the y-intercept to help me figure out what this looked like. So the y-intercept here would have been f of 0, which is 1/2 times 0 minus 2 cubed, which is 1/2 of -8, which is -4. So if I had done that a little bit better, right, I would have gotten that point there, and that would have helped me kind of get the shape of this a little bit nicer. So I know we're out of time. I should stop talking because it is 10:52. But what I'll try and end with here is use the tools you've got, right? You don't have to kind of super strongly adhere to all this. You should be aware of how transformations work, but I wish I had a better thing to say here. There's something here. Try to do graphing with the minimal amount of work you can. I don't want you to work harder than you have to for this.